Okay, this might not be brilliant because I've not used this laptop to record one of these before and I've got a COVID headache, but we will give it a go. So, um, if we want to measure further away, then we can manage with parallax. Then we need what are called standard candles, i.e. something that we know exactly what its brightness is, something that we know exactly what its absolute magnitude is. And the clue for what we could use as standard candles was found by Henrietta Swan Leavitt in 1912. And when she worked on Cepheid variable stars in the Giant Magellanic Cloud. And that's her graph from her 1912 paper there. She found that their brightness correlated with their with the time period of their oscillations. So that's log of time period of the oscillation on the bottom and brightness up the side. And with that information, you can then, if you know how far away a Cepheid variable is, you can then double check for what absolute magnitude is, and then as soon as you know that, you can then scale Swan-Leavitt's graph, and as soon as you can find a Cepheid variable, if you can measure its time period, you can then go back to her graph and her formula and work out how bright that Cepheid variable is, and you know its absolute magnitude. Hopefully that makes sense. Edwin Hubble took her work and applied it to what at the time were thought to be nebulae. And it turns out that when he found Cepheid variables within things like the Andromeda Nebula, he found that actually it was very, very much further away than the stars around about it. It wasn't on a scale of parsecs or even kiloparsecs, it was on a scale of megaparsecs away. And he established that these things were separate galaxies. At the same time, he measured the whether these galaxies were red or blue shifted. And you can see from his graph there, I know it's not a very good graph, but you can see from his graph there that the vast majority of them are red shifted. There's a few in the bottom there that are blue shifted, that are below zero on the velocity axis, and that's because they're gravitationally bound to us. But he found that the vast majority of galaxies were red shifted. And of course, being a physicist, because he'd got distance and because he'd got redshift, or rather the axis on there is the velocity they're going away from us in kilometers per second, he plotted a graph. And I look at that data and think his graph was a bit of a punt, but as they added more and more data to it, it found that the straight line was indeed true, and so we get Hubble's law, which says that the velocity that a galaxy is going away from us, in general, some of them are gravitationally bound to one another, and so are doing more complicated than just going away from us. That's true for the ones in the local group that are coming towards us, but it's true for some of the ones in I think called the Virgo cluster. They're all gravitationally bound to each other, which means that some of them are actually going away from us faster. Some of them are coming towards us because they're all being pulled in towards one another, and that's what that sort of lump in the middle of Hubble's graph is, I suspect. Anyway, it gives us Hubble's law, which is the speed it's going away from us is Hubble's constant multiplied by the distance. And distance is in megaparsecs and speed in kilometers per second, so not usual SI units by any stretch of the imagination. And your datasheet gives you a value for Hubble's constant. It's 65 kilometers per second per megaparsec. So this is an extended version of Hubble's graph, much later than his 1929 one. You can see on the notes there that it says it's got 1,355 galaxies on it, and there's some scatter, but it's a pretty convincing straight line. It certainly convinced a biologist, you can definitely put a straight line through the middle of that and take a definite correlation. Now, dimensionally, if you have a look back and think about Hubble's constant, you've got kilometers per second divided by megaparsecs. Well, kilometers and megaparsecs are both distance, so that means the distance cancels out and you're left with per second. So Hubble's constant is 1 over a time, and it's a constant, so it's a particular time. But what is that time? Well, it's the time when all these objects were in the same place. In other words, It's the age of the universe. It's how long since all of these galaxies were all in one single dot, all together in one place. It's the age of the universe. So the age of the universe is 1/65. Of course, 1/65 is not very helpful, and the reason is that the units are nonsense. So we have to sort the units out. I've jumped a few steps there in that I've said that a kilometre is 3.24 times 10 to the minus 20 megaparsecs. You'd probably have to work it in kilometres and parsecs, and and then convert it into megaparsecs. But I've jumped a few steps and gone straight to that, which means that the age of the universe is that. That'll sort the units out for us, and when you do that sum, you get 475 times 10 to the 15 seconds. And if I convert seconds into years, then I get something that has some meaning to us. The age of the universe is 15 billion years. Now, I've jumped some steps there. You guys can't jump those steps. You've got to lay that out nicely if you're asked to demonstrate this in an exam question. Right, if we want to go further back in the past, because you realise that as we look further and further away over bigger distances, we're looking back in time, because light takes a time to travel. So if we're talking about things that are megaparsecs away, then we're talking light taking millions of years to get to us. If we want to look even further back in time, as close as we can to the early universe, then we need something brighter than a Cepheid variable, because you're not going to be able to resolve a Cepheid variable out of all the stars in a galaxy if that galaxy is very distant. And it turns out that type 1a supernovas do that for us. Now, type 1a supernovas always peak with an absolute magnitude of minus 19. You can see in the graph there, it's actually a fraction over minus 19, but minus 19 does for your exam board. The mechanisms for what a type 1a supernova is, how it's different to a type 2 core collapse supernova, is something that I've covered in more detail in my video that is called the Cosmic Distance Ladder. So if you haven't watched the Cosmic Distance Ladder one and you don't know anything about type 1a supernovas, then I suggest you watch the Cosmic Distance one. Most important thing is that you need to be able to sketch this graph and add values to the axes. So on the axis there, 0 is marked as where the peak occurs, and so the supernova actually starts happening before 0, before the peak, and the supernova lasts for sort of 300 days, 400 days beyond that. So you've got to mark minus 19 on your absolute magnitude scale, and you've got to mark sort of minus 50, 0, and 300 on your time scale in order to get the marks should this turn up in an exam question. Okay, so our type 1a supernovas allow us to hugely extend the Hubble graph. This is the Hubble graph hugely extended with having some type 1a supernovas added to it. The axes have been reversed from the one we were looking at earlier on. Z is redshift, so now we've got the recessional velocity or redshift along the x-axis, and we've got distance on the y-axis. So it's not quite what we were looking at before. And you can see, at lower redshifts, it's still Hubble's nice straight line. But as we get to high redshifts, it starts to curve away. Now, it was expected to start to curve away because we expected that if we look far back in time, we would be able to see the effect of the fact that the growth of the expansion of the galaxy, of the universe, not the galaxy, of the universe, is being slowed down by the drag of gravity. And of course, that's why these scientists did this research, is that they wanted to find out how much gravity was slowing down the expansion of the universe. The shock is that the curve is in the other direction. It curves the wrong way. The universe's expansion isn't slowing down, it's accelerating. Now that's totally nuts. And this is only discovered, I think the paper is 1998, 1999, and has already been awarded the Nobel Prize, which is quite fast for a Nobel Prize to be awarded, because it's such a dramatic thing to find out that the universe's expansion is accelerating. Because if accelerating, what's pushing? we don't know what's pushing. We can understand gravity slowing things down. We've got a force for that, but acceleration requires a force going the other way, and we haven't got a force going the other way. And so what we have is some unseen component of the universe which is forcing the universe apart. And when they fit the curve, and then you can see that fitting is an interesting thing with that curve. You can see some goes at fitting it in my example graph there. What best fits is the assumption that the amount of dark energy, which is what we're talking about here, the amount of dark energy within the universe is proportional to essentially the volume of the universe. So as the universe expands, the amount of dark energy included within the universe gets bigger. Which is the other way around from the way you'd imagine, because you'd imagine that as the universe expands, everything gets diluted. As the universe expands, it has an amount of mass and energy in it, so as it gets bigger, the energy density of the universe goes down. And that's not what they find with dark energy. With dark energy, they find as the universe expands, the amount of dark energy goes up. As we include more volume within the universe by the universe expanding, we include more dark energy within the universe, which is why dark energy is becoming is having a noticeable effect for us now, because the universe got big enough for its expansion to start having an effect. It wasn't necessary in physicist models of the very early universe, where they believe they got pretty good models of the early universe, because in the early universe there wasn't enough volume for the dark energy to be having a significant effect. In the late universe where we live today, the volume is big enough for dark energy to start having an effect. So, called dark energy. Dark because it doesn't show up in our telescopes. Energy rather than force. The vacuum does have an energy, but it's just too small to be dark energy. But energy and force, are sort of two faces of the same coin. Force produces work, and work is energy. Okay, so that was dark energy, and then we have dark matter. And here we have another one of the pantheon of women who lots of people think should have got a Nobel Prize. This is Vera Rubin, and it's Rubin with an I. I think I spelled it with an E later on. This is Vera Rubin, and she and her co-workers published a paper containing this graph that you can see on the right here. Excuse me. Now this is the rotational velocity of spiral galaxies as you get further from the center of a spiral galaxy. Now hopefully you've got a picture in your head of a spiral galaxy. A spiral galaxy has a big bulge of stars in the center. We now know that that center contains a supermassive black hole, and for part of the work on that is what Getz got her Nobel Prize for. So we have this huge mass of this huge bulge of stars and the supermassive black hole in the center of a spiral galaxy, and then we have the spiral arms distributed around the outside. And so what Rubin does is Rubin measures the rotation speed of the spiral arms using the same sort of redshift and blueshift that we've been talking about all along in the last few weeks. As she plots the graphs, and nice looking graphs, as you get further out from the center, the rotational velocity levels off. And it looks like it does that pretty consistently, with no, not a whole lot of variation from one galaxy to the next, which is, a really interesting result. So, you look at that, you go, yeah, okay. But of course, you've got to remember all of the stuff that we've already done on gravitational fields and on motion orbits due to gravity. We're assuming, Rubin was assuming, that the spiral arms are in orbit around that central bulge. Now, if the spiral arms are in orbit around that central bulge, then they've got to be obeying orbital mechanics, and we've done the maths for orbital mechanics. We know that as you get further from the center, the gravitational field strength goes down, and therefore the speed of the object has to go down, because for it to be in a nice stable orbit, your centripetal force is given by your gravity. Well, if your gravity is going down, then the necessary centripetal force is going to be going down which means that your velocity's got to be coming down. And that's encapsulated in Kepler's law. Whatever that says, my brain's hurting at the minute, so something like r cubed is proportional to t squared. And so, think about it. We've done loads of this stuff. Mercury is zipping around the sun, and it's taking very short time to go around the sun. Not just because it's close in and therefore following quite a short circle, but also because it's having to move the fastest, so that its centripetal force balances the large gravity, or its centripetal force is equal to that being provided by the large gravity that close to the sun. Pluto is trickling round because the centripetal force it needs to do its ellipse is quite low. It's a long way from the sun. God, I didn't do a very good job of that, did I? Anyway, I hope you get the idea that those curves are supposed to drop off. They're supposed to obey Kepler's law. The rotational velocity is supposed to go down with distance, not flatten off. It flattening off is a ridiculous result. In no way should it do that. It must have shocked Rubin and her team when they discovered that, because that's just an amazing result that they all give those flat lines when they should be falling off as you get further and further away from that central bulge. So we have the what's known as the galaxy rotation problem. Now we have a second problem that's actually a bit older. This text here didn't come from me. I've pinched it off a website, so I'm not going to read it all out to you. By all means, sort of pause the video and read it yourself. But this comes back to 1938. This is the Comma cluster, and within the night sky there are various clusters of galaxies. It's something that I've perhaps talked to you about in lessons, about the fact that mass comes in lumps. You think about an atom, all the mass is in the middle, and then there's a great lot of empty space around about it. You think about the solar system, all the mass is in the middle, and there's a great lot of empty space around about it. You think about a galaxy, all the mass is in the galaxy, and there's a great pile of empty space all around it. Well, it turns out that galaxies come in clusters, and those clusters, all the mass is in the cluster, and then there's a great pile of empty space around about it. And so Zwicky, again, using exactly the same redshift and blue shift techniques, exactly that, find a spectral line and see how that spectral line has moved, that we've been talking about all along, trying to work out what the velocities of the various galaxies in the Comet cluster were. He made some assumptions, which are discussed there, but basically trying to work out, based on sort of Newtonian mechanics, how much mass there must be within the Comet cluster for the Comet cluster to be moving the way that the Comet cluster must be. And the way you estimate mass for a galaxy is basically you look at its brightness, and your brightness tells you roughly how many stars it contains. If you know roughly how many stars it contains, you know roughly how heavy each star is going to be. You can make a bit of a guess at how much extra stuff, like the solar system, things that is around that star, but basically not much. The mass is in the star, and so you can make an estimate of the mass of the galaxy once you know the galaxy's surface brightness. And so he adds up the mass of all of these galaxies that he's got in his Comet cluster, and he compares that to his mass as to how much mass he thinks should be in the Comet cluster, given how the Comet cluster is moving. And he finds out that the mass he can see is only 1/10 of the mass necessary to produce the observed motion. So, second huge problem to do with galaxies and mass. The solution is, God, that went funny. The solution is dark matter. So the current belief is that galaxies are embedded in halos of dark matter. So you can see sort of an image there of the halo, sort of around about the spiral galaxy. And that halo is distributed in such a way that it explains the motion. Its mass explains the motion of the stars within the galaxy. They're all being pulled about by not only by the mass of the central bulge, but of course they're also being pulled by the mass of the dark matter halo. And the combination of those two neatly deals with Rubin's curves. And so a lot of the mass of the galaxy, or more than the majority of the mass of the galaxy resides in the halo. Now, if there was only one problem, then dark matter being the solution, some made up stuff that we can't see that's called dark because we can't see it in our telescopes, would be ludicrous. But the fact that there's two problems, there's actually three, because there's also gravitational lensing. There's these multiple problems, and the same amount of dark matter that solves Rubin's problem also solves Zwicky's problem, is enough to convince most scientists that dark matter must be true. If dark matter only explained one or other of those two problems, most people wouldn't accept it. But the fact that it explains both of them, actually all three, because it also explains the gravitational lensing one, means that, you know, most scientists are convinced that dark matter must be a thing. There must be this extra mass in the universe that we cannot detect with our telescopes, distributed in these halos around about galaxies. What is it? Well, most people thought it was going to turn out to be WIMPs, which are weakly interactive massive particles. Particles which strongly interact with gravity, i.e. they've got a lot of mass, but only weakly interact with the other fundamental forces, especially they don't really interact with the electromagnetic force. It's dark. And, you know, you might feel that's a bit outrageous, but then think about it. We already know that there are classes of particles that don't interact with some of the forces. So we know that leptons, for example, don't interact with the strong. We know that neutrinos are weakly interacting with pretty much everything. So forces that don't interact, particles that don't interact with some of the forces, or particles which are weakly interacting, actually is not out of the realms of our understanding of the way particle physics works. Trouble is, once you've defined what these WIMPs must be, then you're, as a physicist, your job is to try and start to design some experiments. And even though they're weakly interacting, they must still interact, which means we've got a chance of being able to produce some experiments that has a chance of detecting them in the same way that we can detect neutrinos, even though they're weakly interacting. The trouble is that there have been quite a lot of experiments running over the last few years which were thought to have a chance of detecting WIMPs that haven't found anything. Plus the Large Hadron Collider was expected to produce some particles that were going to be WIMP candidates. Hasn't found anything. So people who are pretty convinced WIMPs were going to solve dark matter are now starting to scratch their heads a little bit, because all of our experiments are coming up with nothing. Consequently, where before nobody would touch any of the alternatives, suddenly the alternatives are becoming interesting. Suddenly you can get funding to look into some of the alternatives. A fourth neutrino, so-called sterile neutrino, axions. I've no idea what an axion is. I've tried to read it and understand. I didn't understand. Other things are being looked at, even and this is almost heresy as far as most scientists are concerned, even the idea that we might be able to explain what's going on by coming up with slight modifications to Newton's laws of gravity is being considered again. A theory called MOND, Modified Newtonian Dynamics. The trouble with MOND is MOND actually really nicely explains Rubin's rotation curves, but does not really quite as neatly explain the gravity cluster thing. So most people stick with dark matter, because dark matter nicely explains them both. Okay, so let's put this together by just sort of talking about the underlying geometry of the universe. General relativity, that's part of why the MOND is such heresy, is it isn't general relativity. General relativity says mass bends space-time. So if we add up all the mass in the universe, we know how space-time is bent. And there are these three possibilities. It's either a closed universe, which is the top one, which is a sort of equivalent to the idea that the universe can expand back out again and then come back down into a crunch. We started at say the North Pole on that globe there. We're expanding out, and eventually we'll end up back in a crunch back down again at the South Pole. Or the universe is on an open geometry, which is that sort of shape there. You know, I mean, the shapes are ridiculous. You know, you're trying to draw four-dimensional space-time in 2 dimensions on my computer screen, but anyway, it gives you an idea. Most people sort of refer to it as looking a bit like a Pringle. That's open geometry, so that's the universe flying apart. And then there's flat geometry, which is the universe keeping going forever. And sort of the way you measure which one we're on is by drawing triangles on them. And sort of the explanation for that, if you think about drawing a triangle, you know, whatever that triangle might be, sort of going from Jersey up to Shetland and then across to Newfoundland and back to Jersey, you draw on a triangle on a map. That would be a triangle. You measure your angles; they'd be 180 degrees. But of course, if you then drew the same triangle actually on the 3-dimensional Earth, and you measured the angles, because you were drawing it on a curved surface, your angles would actually add up to be bigger than 180 degrees. It'll be that top diagram there. If the Earth happened to be if you happen to draw a triangle on a Pringle, you'd find your angles going to be less than 180 degrees. If you drew it on a flat surface, they'd be 180 degrees. And physicists think about doing these kinds of measurements within space-time to see whether they can determine what the geometry of space-time is. And obviously they are drawing triangles, but they think about how to think about it. And the reason, the current thinking is that the universe is flat. Now, if we add up the amount of matter we can see, you don't get a flat universe. If you add up the amount of universe that we can see and you add in dark matter, you still don't get a flat universe. But if you add in the amount of matter we can see, you can add in dark matter and you add in dark energy, you get a flat universe. So we sort of one more hint that these things are actually true, that dark matter and dark energy really are a thing, that they help us explain the flatness of the universe. But the scary thing is the split. The universe is thought to be getting on for 70% dark energy, getting on for 30% dark matter, and a measly 5% is normal matter. We only understand 5% of the stuff in the universe. Physics has got a whole long way to go, hasn't it? You know, we only understand 5% of the stuff in the universe. Oh my goodness, we have not been doing a good job. Sitting back and smoking your pipe that I was talking about last year, when all this physics got solved at the end of the 19th century. That ain't happening anytime soon. We only understand 5% of stuff in the universe. Anyway, quick summaries of everything I've talked about in this talk. We talked about the cosmic distance ladder, and that's this idea that each bit builds on the one before. So parallax finds the distance to the stars in our galaxy. Parallax helps you confirm the distances to the Cepheid variables and confirm that the Cepheid variables are indeed standard candles. Once you've got standard candles, you can go to longer distances and find the distances to galaxies. And then the Cepheid variables, they allow you to confirm that type 1a supernovas are always go off the same -19 absolute magnitude, because you find some type 1a supernovas in galaxies that you've got Cepheid variables in, and you can get the exact distance of the galaxy. You can measure the absolute magnitude of the type 1a supernova. They always go off with an absolute magnitude of -19. And then once you've got type 1a supernovas to be your standard candle, then you get distances to the far galaxies, not just the nearby ones. There are astronomers at the moment who are trying to work out how we go even further, and they're looking at quasars. Can you use quasars as standard candles? Not easily, but they're trying. And if you plot galactic distance against redshift, or rather, it's actually the other way around. If you plot redshift, the velocity that the galaxies are going away from us, against galactic distance, you get Hubble's law. And Hubble's law tells us that the universe is expanding uniformly. And the reciprocal of Hubble's constant is the age of the universe, once you sort out the units, and sorting out the units is sometimes an exam question. And then dark matter and dark energy. When the Hubble graph was extended back by adding in more distant galaxies, we expected to see its expansion of the universe slowing down. Instead, we found the expansion of the universe accelerating, and dark energy is that thing that is postulated to explain it. And then we have the galaxy cluster problem, and I think I probably misspelled both Zwicky and Rubin, but never mind. And we have the rotation of spiral galaxies problem, and both of those are solved by postulating this mass that we can't see, dark matter, to account for both of those problems. So we have dark energy to account for the acceleration of the universe, and we have dark matter to account for the fact that spiral galaxies don't rotate as they should, and galaxy clusters don't move as they should. And when we add them both up, we led to the understanding that only a very tiny fraction of the universe is made out of normal matter that we understand, and that therefore we've got a long way to go before we really understand the universe.